Welcome back, and let us resume our discussion on sampling. So, last module we discussed the leakage issue with the switch, and we looked into the R off and CS combination, which is ultimately going to determine the size of the CS. What is the minimum value of the CS required to successfully store the sample data over the entire duration. Likewise, we also would like to make sure that the R on and CS factor is also matching our criteria of being less than the T on duration over here, and that will ultimately determine what should be my T on, how aggressively my T on can be scaled down, so that I can use very narrow pulses for sampling my analog data. For that, once again I can just check the numbers. If I use minimum size transistor and assume the R on to be 10K and the C is say close to 1 picofarad, then once again the value that I get over here is going to 10 to the power of minus 6. So, you are having say capacitor of 10 to the power of minus 12, and you are having a TS, which is say duty cycle of the TS you are trying to reduce by say 1 upon 10. So, in that case you are going to have 0.05 millisecond. Now, whether we can go for 1 upon 10 or lower, that of course depend upon this particular value. And if you look at the RC combination, you are having the overall R on given with 10 to the power of 4, and this is going to determine my T on duration. Here I am getting overall factor of 10 to the power of minus 8, which looks like much smaller than the T on duration that we are targeting. Our sampling duration is 0.5 millisecond, and as compared to the R on C combination that we are getting, the T on duration looks like pretty large. As a result, we do have a lot of room for scaling down T on in this case. And in general, for CMOS technology, even if you are using minimum size transistor, the sampling duration can be relatively small for the given capacitor size that we have chosen. As a result, we can aggressively scale down this T on. A duty cycle ratio of maybe just 10 or even lower can be good enough for sampling the data. So, we do have enough room for sampling or reducing the duty factor and sampling the data with very narrow pulses. Only thing that we have to make sure is that the data is stable enough. For that, we have already determined the CS. So, what we conclude out of this is that for a minimum size transistor, we have enough headroom for reducing this T on, and we can go down at least by an order of magnitude and use say a few microsecond of pulse width to do the sampling. So, even if I use 1 microsecond rather than 1 millisecond, we will still be within limit, very comfortably within the limit. So, let us go for 1 microsecond. Why we are not going for lower than 1 microsecond? That has something to do with the generation of this 1 microsecond pulse. So, we will see that when we go for the digital control and all, how these control signals for sampling, switching, etc., will be generated. So, ideally speaking, we can go down further, maybe sub microsecond regime, but for the time being let us choose this 1 microsecond because it is significantly small as compared to our overall sampling duration of 0.5 millisecond. So, if this is close to 1 microsecond, it is hardly significant as compared to the entire sampling period. So, let us stop here. Just a few points regarding the R on. If you are trying to increase the switch widths just to speed up the transistors, there can be other issues that can also come into picture, which relate to the which are related to the non-ideal effects of these switches, and their effects can still be seen even if the switch is minimum size. Their effects can still be seen at the output, and if I am using minimum size transistor, those effects will be smaller. If we go on increasing the size of the transistor, then they become a lot more prominent. That is another reason for choosing a sufficiently large CS. Let us see those two reasons, those two contributors very briefly, and how they can have an impact on the sample data, how they can corrupt the sample data. Remember, the resolution that we are seeking is around 15 millivolts. So, we do not want this signal to be corrupted by more than maybe few millivolts if we want to preserve the signal integrity over here. Therefore, any non-idealities coming from the switches, if it is trying to corrupt this data beyond few millivolts, definitely it needs to be considered. Even if it is minimum size transistor, we must make sure that it is the non-idealities associated with this switch is not significantly distorting the data over here. So, let us look into the two main factors which can distort the data, which is first one is the charge injection, and we will look at the second one, which is clock feed through. So, these concepts are in general very crucial when we are looking for switched capacitor circuits, wherever we are having amplifiers combined with lot of switches and capacitors to implement interesting functionalities like integrators, closed loop amplifiers, filters, and so on. Here we are just talking about the sampling operation, where also these two effects play a very important role and can limit the accuracy that we can achieve by the sampling process. Inherently, we will see that the transmission gate topology that we are using is going to give us advantage in terms of both of these, but it is important to be aware of both these non-idealities. So, charge injection arises because of turning off of the transistor, whether it is NMOS or PMOS. And if I look at this behavior, you have a sampling switch. Suppose I am considering only NMOS and the switch is turning on and then going off. We know that the channel charge in the NMOS, if it is in triode region, it will be almost uniformly distributed in the channel. Source drain are almost equivalent for the triode region when the input is almost equal to the output. And under that condition, I can write down the total channel charge in this MOSFET QCH as W times L times COX times the overdrive voltage, which is going to be VGS minus VT. So, if I say VG, which is the gate voltage when the switch is on, which is VDD minus Vs. The source can be taken as either this one or this one, whether in triode region both the terminals are almost equivalent when the switch is on, and therefore, I can just take it as V in minus the threshold voltage, which is VTN. So, this is the overall channel charge that I can write, and when the switch is turning off, this channel charge is supposed to be ejected out of the MOSFET. So, when the switch turns off, this channel charge gets ejected, and if I assume that half of it gets injected in the opposite directions, I have QCH by 2 jumping on to this capacitor, which is CS. Therefore, the delta Q that I get on the CS, that is going to be Q channel by 2, assuming that the charge is injected equally on both sides after the MOSFET gets off, because remember, when you turn off the MOSFET, the mobile electrons forming the channel charge have to be injected out, so that the MOSFET is turned off, and that injection involves injection of negative charges on both sides, because remember, NMOS is going to have electrons as channels, the mobile charges are negatively charged electrons, and therefore, it amounts to a negative charge injection on both this point. So, this is basically going to be a negative QCH minus sign injected onto the CS, and therefore, what we can expect is that as compared to the V in, the V sample would be V in minus this mod QCH upon 2. Now, this is the delta Q that is injected on the CS. Therefore, what should we expect for the delta V? So, we know that Q equal to CV. So, according to that, we should have a delta V, the change in voltage over here, this delta QCH or QCH divided by CS. So, this is going to be my the voltage. So, ideally should have been just equal to V in, but because of the QCH, it is having this particular magnitude, and if I plug this in, I have this as the positive quantity. So, WLCOX upon 2 CS times VDD minus V in minus VTN, and if I take this common, I am left with 1 plus WLCOX upon 2 CS, and then I have some negative quantity which can be given as WLCOX upon 2 CS VDD minus VTN. This is what we are left with. So, ideally I would expect Vs equal to V in, but I am getting this whole term where I have first of all some non-zero gain factor V in times this gain factor which is greater than unity, and then I have some offset term which looks like independent of the signal to the first order, and definitely that would mean that I am having some corruption in the signal as compared to the sample signal, my data is slightly different. And if I plot these, so ideal curve would have been V s equal to V in, but because of the gain which is greater than unity, I am going to get a slope which is greater than 45 degree, and also we are going to have a negative offset. So, when V in equal to 0, I should have some negative offset. So, as a result, I am going to have the actual curve looking like this. Ideally, this is what we expect. Therefore, I have deviation in the sample signal as compared to the input signal, and of course, we can see that if the area of the switch is increased, that is W and L is increased, and the CS is reduced, then the effect of this channel injection, the charge injection will be much more prominent. So, if you are trying to increase your sampling speed, then of course, the corresponding charge injection effect can be more prominent, it is going to corrupt your data more strongly. So, there is always a trade off between the sampling speed that we are trying to achieve and the charge injected. Remember that this charge injection phenomena is more or less going to be independent of the T on duration, because T on duration or the duty cycle, even if we aggressively scale it down, it does not affect the overall quantity of charge injected. Whenever it is getting off, it will inject the same amount of charge. So, it is independent of the T on of the duty cycle. The duty cycle is not going to affect it. However, the size of the MOSFET and the capacitor, they are going to affect it. So, if I am trying to make my T on if I am trying to make the MOSFET larger or CS smaller in order to facilitate faster sampling, it is going to have more corruption because of this charge injection effect. And we can see that the overall nonlinearity, that is the overall gain error that is coming, is dependent upon the W L C O X upon 2 C S. And if we talk about this quantity W L C O X for a overall, if we are looking at a nominal device of 1 micrometer width, this parameter W L C O X for 180 nanometer technology, L being minimum say 180 nanometer, W being say close to 1 micrometer, this factor can lead to few femtofarads, a few tens of, at the max, few femtofarads. And the CS, if I want this to be this error to be sufficiently small, CS must be sufficiently larger than this. So, for example, if I am talking about say high precision, say 1% or better precision, then of course, I would like this to be at least several hundreds of femtofarad. The other term over here also can be problematic. If I look at this VDD minus VTN, this VTN is also a quantity which is not independent of the signal. So, VTN in general will depend upon the body effect, and if I look at the NMOS where the body terminal is say grounded and you are having the source terminal which is equal to V in. So, ultimately this becomes a function of V in, which is having a highly nonlinear characteristic. So, therefore, it is also going to introduce nonlinearity. In very high precision application, it can be more critical. For our application where the precision is relatively limited, it is still less not so much critical. However, we must make sure that in the overall design, when we are designing the sampling switches, these effects are minimal and they are not violating our precision requirement. For example, in our case, we would like to make sure that the overall the factor resulting over here is not leading to more than say a few millivolts of error in the sampled data. If I talk about the other issue which also comes in because of the clock action, is called clock feed through, and that has to do with the action of the parasitic capacitances associated with the clock. So, if you have a NMOS over here, and if I assume that you have the parasitic capacitances from the gate to the source and gate to the drain in triode region, remember both of these are almost similar, and you are trying to switch this switch on and off by applying that pulse, and you are having the V in over here. Ideally, if these two are absent, and for the time being if I ignore the channel or the charge injection effect, the switch is faithfully going to replicate the V in over here. But now, if I also look at the condition when the switch is almost turning off, under that condition I have an effective voltage divider formed between this C, I can call it CGD of this MOSFET and the CS. So, at the verge of turning off, this switch is, you can assume it is almost an open circuit, and then we have the input voltage over here transiting from VDD to ground. Therefore, we effectively have a capacitive divider where the input signal is transiting from VDD to 0 to turn off the switch, and we have the CS over here. And as a result, if I want to see what is the effect of this voltage transition on this point. So, this is something like an AC divider where because of the capacitive coupling, this step voltage over here is going to have some effect over here. So, if I look at this, it is just going to be proportional to delta V is resulting from this clock action is going to be proportional to CGD upon CGD plus CS. And therefore, once again we can see that if the MOSFET dimension is larger, for example, if you are having a larger W of this MOSFET, once again the CGD will be proportional to the W of the MOSFET. Also, you have in saturation region, you have the overall CGD given by a combination of the oxide capacitance and the overlap capacitance. So, therefore, it is also proportional to the length of the MOSFET. So, in the triode region, remember both CGS and CGD become almost similar, and they are proportional to the CGD is proportional to the 1 upon 2 COX WL plus the C overlap. This term depends upon the W of the MOSFET, and here of course you have WL. So, both dimensions. So, basically if you are having a larger size MOSFET, once again to cater to faster speed, you can expect more corruption, and especially here you are having a VDD which is 2 volt, and you would not like this potential to fluctuate more than few millivolts because of this clock action, and therefore, it becomes critical that this CGD is sufficiently smaller than CS, 1000 times smaller than CS. So, once again this is going to impart some limit on the some lower limit on the value of CS. If you want to have sufficient accuracy for the data sampling, I would like the CGD to be orders of magnitude 1000 times smaller than CS, and that would again imply that if I talk about the minimum size transistor also, even if I am using minimum size transistor with WL minimum and it is having few femtofarads of parasitic capacitances, that would imply that the CS must be at least few picofarad to ensure that the signal is not significantly corrupted because of this delta V coming in. So, once again we can see that these constraints related to the non-realities of the switch are going to play a significant role in determining the sizing. So, even if you are looking at low frequency application where the size of the MOSFET can be afford to be small, we should be careful about these effects, and that is going to that is going to increase the lower limit for CS. So, first limit came remember from the leakage. We are looking at the leakage, and that should not cause sufficient droop in the output sampled voltage as compared to the ideal value, and there are other two components also coming in because of this clock action term, which is termed as clock feed through, and the other one charge injection. Why it is called clock feed through? Because the clock it is transiting at this gate of this MOSFET, but because of the parasitic capacitance you are having feed through of that voltage because of this capacitive coupling. So, if you connect two capacitors in series and you are having a large jump at this point, of course, you will see some fluctuation at this point because of this capacitive voltage division, because remember this transition point is going to have high frequency component, it is not. So, and because of that high frequency component, definitely you are going to have the corresponding signal propagating at this point because of this voltage division. So, we have to be definitely careful about these two, and another one important factor is that if you are using transmission gate based MOSFET, there to some extent this both charge injection and clock feed through can be minimized, because remember the PMOS and NMOS actions are just opposite. When the NMOS is getting on, PMOS both the NMOS and PMOS are getting on, the gate voltage of one of them is going to VDD, another one is going to ground. Therefore, the polarity of the gate voltages or the clock waveforms are just opposite, and to some extent they can cancel the effect of clock feed through as well as charge injection. It depends very much upon the MOSFET parameters, and it is very difficult to exactly match them and cancel them out, but to some extent of course transmission gate can help in minimizing both these effects, that is the clock feed through and charge injection, because of the opposite polarity of the clocks applied to the gates of this MOSFETs. So, you can again look at the combined structure where you have the PMOS and the NMOS, and you are having the charge injection effect as well as the clock feed through over here, and you have the sampling capacitor CS, and you have the V in coming in from here. And remember, if I talk about the clock action for turning off this MOSFET, the clock will be going in the negative direction, whereas turning off the PMOS, it will be going in opposite direction. So, the effect of clock feed through, if I assume this equation, is just opposite. On one terminal you are having the signal going from 0 to VDD, another one VDD to ground. Therefore, to some extent it can get cancelled if these capacitances are almost similar, and in order to make this similar, it will be important to make them almost same dimension. However, it may not be able to exactly cancel that out. It is not always possible to have exact matching between these two, but to some extent it can definitely reduce. Likewise, if I talk about the charge injection for the NMOS, as we said, it is going to inject negative charges, right. So, whenever it is turning off, the electrons which are forming the channel of the NMOS will be injected on the opposite side. PMOS is having holes in the channel, right. So, that effectively means vacancy of electrons. So, when the PMOS turns off, the holes get injected physically, of course, electrons get injected into the PMOS channel to kill the channel. As a result, the NMOS is going to dump electrons, whereas PMOS is going to sink electrons when the channel gets off. Therefore, it will also try to cancel out this effect to some extent, and therefore, once again you can have some cancellation. To some degree you can have some cancellation. Of course, if you look at the charge stored, the equation of the charge stored, if you can see for the NMOS it is going to be VGS. So, if I assume that this particular potential is V in, for the NMOS we have seen the Q channel of the NMOS is going to be COX W times L times VGS minus VT. So, VG is VDD minus Vs is V in minus Vtn, and the Q channel for PMOS, if I look at this again, L times COX times W, for that it has to be VSG. So, if I say VSG, so Vs becomes V in and gate becomes 0, because when the PMOS was on, Vg was 0. So, and Vs was V in, and then you have minus mod Vtp. So, this is the magnitude of the PMOS charge, because for PMOS when the channel was on, it was the VSG. S is the input voltage or the sample voltage over here, both of them being similar, and the G is 0 for the on condition. Therefore, VSG becomes V in minus 0 minus mod Vtp, and therefore, if you see the magnitude point of view, it may not cancel exactly, because you have two different terms over here. Only for certain value of V in it will cancel, but at least to some extent, roughly it can minimize the charge injection effect to some extent. There are other schemes people do apply, like rather than depending on this NMOS and PMOS pair, if you also add additional dummy transistors over here. For example, for the NMOS, if you end up adding a dummy transistor, these are source and drain which are shorted together, and then you are having the W, and then assume that this W is half of the NMOS over here. So, this is, if this is W1, this is M2. So, what I am doing is I am shorting the source and drain, and this is the gate. I am applying just a clock bar over here. So, when this turns on, this turns off, this turns on. So, basically when if I assume that W by L2 is W by L2 is half W by L1, this dimension is just half the dimension of this one. That means, if I assume that half the channel charge is injected over here, that can be used in forming channel of this NMOS also. This is very well matched with this particular NMOS. Likewise, if I put a PMOS dummy device that is having W which is just half the W of this PMOS, when it turns off, I will turn that one on. So, I can have another PMOS device dummy. I can short the source and drain. So, the source and drain is shorted, and if I am feeding clock here, I will feed clock bar here. If I am feeding clock bar here, I will feed clock here. So, that when this NMOS is turning off, this dummy NMOS is turning on, and it will just sink that charge, because if this is injecting the charge, this channel is getting killed, its channel is getting formed. So, it will just sink that charge. Likewise, the PMOS over here, when this is getting on, when this is getting off because of the 0 to VDD transition, it is injecting the holes, whereas this is getting on because I am driving it by clock, and as a result it will be injecting those holes to form its channel. So, when its channel is getting killed, it is forming the channel. Likewise, when its channel is getting killed, this one is forming the channel, and if their dimensions are matched, W by L of this being half of W by L of this one, likewise W by L of this being half the W by L of this one, it can help in mitigating the charge injection to some extent, provided we have almost half charge injected on both sides, which is not always true. Also, we can see if this configuration can also help us in mitigating clock feed through, because if I look at the capacitance for one of these devices, so the CGD of these devices will be the combination of CGS and CGD, the total capacitance, and the W of this one is half the W of the PMOS over here. This capacitance and the total capacitance provided by the parasitics over here will be similar. So, I am assuming that if this is 3 and this is 4, W by L of 4 is half W by L of 3. Under that condition, once again these two capacitances combined together will be equal to the capacitance over here, and as a result if I look at the condition, I have clock transiting from 0 to high over here, but here you have just opposite transition, you are applying the reverse clock over here, and as a result if I look at the total signal over here, at this node I can model it as the first capacitance having a transition from 0 to VDD, and the second capacitance, total capacitance provided by the MOSFET over here, which is having transition from VDD to ground, and then I am having the total capacitance over here CS. So, these two will be almost similar because the W by L of this one is half of this one. So, the CGD and CGS combined for this MOSFET is going to be same as the CG D of this MOSFET, assuming that in the triode region both are almost similar. So, in that case I can see that the overall effect of 0 to VDD transition and VDD to 0 transition will be almost cancelled out because of the equivalent CGD appearing over here, and then the overall effect can be cancelled out. Likewise on the NMOS side, and because this NMOS, these transistors are the source and drain are anyway 0, say so in terms of static current they are not having any static current, they are just going to sink the current, little bit of fraction of current when the channel gets on, and again eject the current when channel gets off, and their action is opposite to these two. So, they are not of course having any static current. So, they will be having only transient current just to form the channel and kill the channel. So, these methods can be used to mitigate the effect of clock feed through and charge injection to some extent, especially when we go for high speed circuits where the switch dimensions becomes critical and the CS has to be smaller. This becomes very handy. We can see later that if you are using fully differential circuits, the effect of these two phenomena can be mitigated further. So, here we are having single ended circuit. If you are using fully differential circuit, the effect can be mitigated to a larger extent. For example, if you have a fully differential implementation, you are having two CS1 and CS2, and the input signal is also fully differential, V in plus and V in minus. Then these offset terms that come over here because of charge injection and clock feed through can be cancelled out to some extent. Of course, there is nonlinear dependency on V in, just we saw that. So, it will not be ideally cancelling out fully, but to some extent a fully differential implementation even for the comparator can help in killing this non-idealities. So, that is one of the reasons why people prefer fully differential, even fully differential comparators and fully differential ADCs, so that the non-idealities of these switches can be mitigated to some extent, and especially when you go for high precision circuit where the precision becomes a lot more critical, or you need to do some very sophisticated DSP in the digital domain for which you need very precise analog data. For that I would like to cancel out these effects of these non-idealities, but in that case I would like to make even my ADCs or the comparator fully differential. Right now whatever comparator we are going to discuss probably is going to be, first version is going to be single ended differential input but single ended output, but later we can see how to extend it into a fully differential comparator which will be applicable for the processing of a fully differential signal as well. Alright, so we can take a short break and then start our discussion again.